y'all, it's Sarah. Welcome back to the Applications of Differentiation chapter of my Calculus 1 series. Today we are talking about curve sketching. So I'm going to go over the basic process of it, and then we'll spend most of the video doing two examples. These examples do take a long time. Any of these problems are going to take a while. There's a lot of steps to complete, so bear with me. So the first thing that you have to do is just find the domain of the function. So that is the values of x for which the function is defined. And then we find the x and y intercepts. Then we look for symmetry. So even and odd functions, we do that by plugging negative x into the function and seeing what we get. And then periodic functions, that would be like trig functions are an example of periodic functions, where like if you plug in x plus a certain number, you get the same thing as if you didn't add that number, just f of x. Asymptotes, so we look for vertical asymptotes by setting the denominator after crossing out any holes equal to 0. So rational functions, we'd have to cross out holes. Officially, it's going to be any point where the limit as x approaches that point from the left or from the right is equal to positive or negative infinity. And then horizontal asymptotes, we take the limit as the function as x approaches infinity and as x approaches negative infinity. And if those limits are not infinite, then we're going to have a horizontal asymptote. For increasing and decreasing intervals, we use the increasing-decreasing test. To find local maximum minimum values, we use the first derivative to find the critical numbers of f, and then we use the first or second derivative test. And then for concavity and inflection points, we find the inflection points of f, which is where the second derivative is equal to 0, and then we use the concavity test. All right, so we are going to move on to our first example. So the first thing that we want to do here is find the domain of the function. So this is a rational function, and so to find its domain, we say that the denominator cannot equal 0. So we subtract 9 from both sides, and we get that x squared cannot equal negative 9. Now to solve for x, we'd have to square root both sides, and square rooting a negative number is not allowed in the real numbers. So this is impossible. It's impossible for there to be any restriction on the domain, which means the domain is all real numbers. Next, we move on to intercepts. So to find the y-intercept, we plug 0 into the function, so we find f of 0. So that's going to be 0 over 0 squared, which is 0, plus 9. 0 over 9 comes out to 0. So our y-intercept is going to be 0, 0. And then to find our x-intercepts, we set the whole function equal to 0. So, and you can only have one y-intercept, but it's possible to have multiple x-intercepts. Now, we multiply both sides by the denominator, and we get x equals 0. So, our x-intercept is the same as our y-intercept. It's 0, 0. Now we're going to move on to symmetry. Now with rational functions that don't involve any sort of trig function, we're not going to really have to look for anything periodic, but we do need to look for whether it's even, odd, or neither. So we plug negative x into the function. So we have negative x over negative x squared plus 9. That's negative x over x squared plus 9, which is just negative f of x. So that means that our function is odd, and odd functions are going to be symmetric about the origin. So that'll come into play when we're graphing the function. The next thing we need to worry about is asymptotes. So, for asymptotes, the first thing we want to do is, after crossing out any holes, which here there aren't any, we want to set the denominator equal to 0. So this is very similar to how we found the domain, right? X squared plus 9, here we're saying equals 0 to solve for any places where it does equal to 0. X squared equals negative 9. Again, we can't solve for x here, right? So there are no vertical asymptotes. For horizontal asymptotes, we want to take the limit as x equals infinity as x approaches infinity, and then we'll take the limit as x approaches negative infinity of the function. So here we want to multiply by 1 over x squared over itself, because x squared is the highest power in this rational function. So we have the limit as x approaches infinity of 1 over x over 1 plus 9 over x squared. So now we can plug in infinity. We have 1 over infinity over 1 plus 1 over infinity. 9 over infinity, and infinity squared is just infinity. 1 over infinity is 0. 9 over infinity is 0. So we have 0 over 1, which is 0. So we do have a horizontal asymptote going towards positive infinity at 0. Now we need to look at what's going on approaching negative infinity. Now, with negative infinity, we do the same thing, except if we were multiplying by 1 over an odd power of x, we would multiply this by negative 1, right? We'd make the whole limit negative. But here, x squared, that's an even power, so we don't have to do that. So we're going to get the same thing as we did above. And so again, it works out the same way, and we get 0, because it's an even power. The limit going to positive infinity and to negative infinity are the same. So we have a horizontal asymptote at y equals 0 on both sides, right, going towards both positive and negative infinity. The next thing that we want to talk about is where it's increasing and decreasing. To do this, we're going to use the increasing-decreasing test. So, the first thing that we need to do here is we have to find the places where our first derivative could change sign in order to see where it's positive and negative. So that's finding critical points. So the first thing we have to do is just find f prime. So we are going to use the quotient rule here. So it's low d high minus high d low over low low. So we have the denominator, which is low, times the derivative of the numerator, derivative of x is 1, minus the numerator, so just x, times the derivative of the denominator, which is 2x, and then that's all over the denominator squared. So when we distribute everything out, we get x squared plus 9 minus 2x squared over x squared plus 9 squared, which is 9 minus x squared over x squared plus 9 squared. So we set that equal to 0 in order to find the critical points. So we multiply both sides by the denominator, and we get 9 minus x squared equals 0. So x squared equals 9. So we square root both sides and get that x equals plus or minus 3. So we're going to have critical points at x equals negative 3 and at x equals 3. Now, what I like to do here is just draw a number line. And I'm going to put negative 3 and 3 on there. I need to make this a little longer, don't I? For this one, I'm doing it to scale. I usually don't. So I want to figure out whether the derivative, whether f prime, is positive or negative in each of these ranges. So first, I want to figure out what's going on here. And so I'm going to plug in a number that's less than negative 3. I'm choosing negative 4. So we just plug that in. And all you have to do here is get to the point where you realize whether it's going to be negative or positive. So go as far as you need to realize that this is negative. So everywhere from negative infinity to negative 3, our first derivative is going to be negative. Next, I'm going to plug in something between negative 3 and 3 to figure out what's going on here. I'm going to choose 0 just because it's easy. So clearly, this is going to be a positive number. And then finally, I have to figure out what's going on from 3 to infinity. So I'm going to choose 4. So this is the same as f prime of negative 4, right? It's negative. So what this tells us is that our function f is going to be decreasing wherever f prime is negative. So that's from negative infinity to negative 3, and from 3 to infinity. And then it's increasing whenever f prime is positive. So that's from negative 3 to 3. All right. The next thing that we want to do is find local maximum and minimum values. So I'm going to use the first derivative test for this problem. And in the second example, I'll use the second derivative test. So basically, the first derivative test is really easy to use after you've already done the increasing decreasing test, because it's basically the same information, right? So the first derivative test tells us that whenever our derivative goes from negative to positive, we have a local minimum. So based off of this number line, at negative 3, we're going from negative to positive. I always draw a little picture. Okay, we're decreasing, then we're increasing. That'd be a minimum. So we have a local minimum at x equals negative 3. And just for graphing purposes, I want to actually know the value at that point. So I'll find f of negative 3, which is negative 3 over negative 3 squared plus 9. That's negative 3 over 9 plus 9. Negative 3 over 18. That's negative 1/6. So our local minimum is at the point negative 3, negative 1/6. Now, also by the first derivative test, when we move from the derivative being positive to the derivative being negative, like at 3, we're going to have a local maximum. So we have a local maximum at x equals 3. And again, I want to actually know the value of the function here. So I'm going to plug this in. And I get 1/6. So our maximum is at the point 3 1/6. All right, next we want to move on to concavity and inflection points. Which I shorten as POIs for points of inflection. So if you remember, f prime looked like this. It's 9 minus x squared over x squared plus 9 squared. We want to find f double prime. So that's going to take the quotient rule again. So low d high, so the denominator times the derivative of the numerator minus high d low. So the numerator times the derivative of the denominator, which here we actually have to use chain rule. So just the derivative of something squared, we take down the 2, and then we just have this. And then we have to chain it with the derivative of x squared plus 9, which is 2x. And then low squared. So x squared plus 9 squared is going to be now to the 4th power. Then I'm going to distribute things out. So just kind of clean this up a bit. All right. Now notice that we have an x squared plus 9 here, we have an x squared plus 9 squared here, and to the 4th here. So we can pull out an x squared plus 9, just not squared, just x squared plus 9 we can pull out. And so when we do that, here's what we get. We're still left with an x squared plus 9 here, but in the second term it just goes away. And on the bottom, it becomes to the 3rd power. Now we want to distribute everything out. So we get negative 2x cubed minus 18x minus 36x plus 4x cubed over that same denominator. And then we can combine like terms. And here's what we end up with for our second derivative. Now, in order to find our inflection points, we need to find the places where the second derivative is equal to 0. So let's go ahead and just set this equal to 0. So we multiply both sides by the denominator. So now we can just say, okay, the numerator needs to equal 0. So what I'm going to do here is factor out a 2x. So now we know we have either x equals 0 or x squared minus 27 equals 0. So that would mean x squared equals 27. So then x equals plus or minus the square root of 27, and we can simplify the square root of 27 because it has a 9 in it, and that's a perfect square. It can become plus or minus 3 root 3. So we have inflection points at x equals negative 3 root 3, x equals 0, and x equals 3 root 3. So I'm going to go ahead and draw a number line here. This time it's definitely not going to be to scale. Now, in order to plug in numbers into f double prime that are in each of these intervals, we need to know what's going to be greater than or less than 3 root 3 and negative 3 root 3. 3 root 3 is approximately 5.2. So this is around negative 5.2, and this is around 5.2. So like if we want to plug in a number in this interval, we can do negative 6, and that's what I'm going to choose. So clearly we're going to get a negative number here, right? Because 432 is bigger than 324. It comes out to negative 108 over 45 cubed. So this is going to be negative, which means everything from negative infinity to negative 3 root 3, f double prime is negative. Now I'm going to do something in this range. I'm going to pick negative 1. Negative 1, 1, and 0 are usually really easy numbers to pick. So this becomes 52 over 10 cubed, which is positive. Next, I'm going to plug in something in this interval. I'm going to pick 1. So now I'm going to get negative 52 over 10 cubed. So that's a negative number. And then I need to plug in something over here. I'm going to choose 6. I always like to choose, like I did negative 6, now I'm going to do positive 6. The numbers are going to be the same. I'm just going to be changing the signs of things, so it makes it easier. So now it's the other way around. I have 432 minus 324 over 45 cubed. And obviously this is going to be positive because 432 is bigger than 324. So yeah, it comes out to a positive number. So for everything from 3 root 3 to infinity, our second derivative is going to be positive. Now we use this number line and we're concave up everywhere that the second derivative is positive. So we're concave up wherever we have a plus sign. So here, that's from negative 3 root 3 to 0, and from 3 root 3 to infinity. And then we're concave down wherever there's a minus sign. All right, so we have completed our checklist and now we are ready to graph. I drew this not quite to scale just because we have some kind of strange numbers here, but basically to start, what I like to do is kind of work from left to right, and remember that because this is symmetric about the origin, whatever we do on the left, we'll flip it over, like flip it over the line y equals negative x in order to construct the other side. So we know that our x-intercept and our y-intercept are both 0. So we can go ahead and plot the point 0, 0. We know that our graph will be going through that. On both sides, we also have a horizontal asymptote at y equals 0. So I'm just going to dot that in. So as x approaches infinity and as it approaches negative infinity, our graph has to approach 0. Now, we have a maximum and a minimum, right? Our minimum at negative 3, negative 1/6, and our maximum at 3, 1/6. So I'm going to plot those. All right, now let's talk about where our intervals of different concavity and increasing and decreasing coincide, right? So negative 3 root 3, that's around negative 5.2. So what's happening from 0 to negative 3 applies there, right? From 0 to negative 3, we are going to be decreasing because of the increasing decreasing test. And because of the concavity test, we also know that we are going to be concave down. So up until that point, we're approaching this axis, we're decreasing and concave down until around, and I need to not be that steep, until around negative 5.2. At negative 5.2, we're still decreasing, but we switch to concave up. And then at negative 3, we're going to switch to increasing, but we're staying concave up. So you can see how each of these components of like aspects of the graph that we've figured out help us to actually build what the graph looks like. And then we reflect this about the origin. So we're going to have increasing and concave down here, and then decreasing and concave down until around 5.2, at which point we switch to being concave up while still decreasing. So this is our graph. A lot of things to keep track of, but in the end it allows you to graph something accurately, accurately enough without having to plot every point that you want to represent. All right. Now we have a new function. This one, we are given a domain restriction, okay? So we know that tangent is a periodic function, and after, from negative pi over 2 to pi over 2, it repeats the same thing, over and over again. So because we have this domain restriction, when we're looking for the domain, all we have to do is check if there's any points in between negative pi over 2 and pi over 2 that also would not be in this domain. So I don't tend to, in a test situation, remember the places where tangent is undefined off the top of my head. And so what I like to do is think of it as sine over cosine, right? This is going to be sine of x over cosine of x. So that's going to be undefined whenever we have to divide by 0. So in our domain, cosine of x cannot equal 0. The zeros of cosine are a little easier to remember, to figure out in the moment. So it's plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, and so on, for every odd multiple of pi over 2. So none of those are in the domain anyway, right? From negative pi over 2 to pi over 2, not inclusive. So this doesn't actually change anything about our domain. Our domain is going to be negative pi over 2 to pi over 2. Now, the next thing we have to worry about is intercepts. So to find our y-intercept, we want to plug in 0 for x. So f of 0 equals 0 times tangent of 0. Obviously, we're multiplying by a 0. Tangent of 0 also happens to be 0. So this is 0. So our y-intercept is going to be at the point 0, 0. And then for our x-intercept, we want to set the function equal to 0. So x times tangent of x equals 0 means either x equals 0 or tangent of x equals 0. So again, this is sine of x over cosine of x. So if you don't know the zeros of tangent, you can figure out this way too. We can basically replace it with sine of x over cosine of x, multiply both sides by cosine of x. So we have sine of x equals 0. And those zeros are a little easier to remember. So those are going to be 0, plus or minus pi, plus or minus 2 pi, and every other integer multiple of pi. Notice that, though, the only one of those that's actually in our domain is 0. So that's still our only x-intercept. All right, the next thing we need to move on to is symmetry. Now, when you see that there's a tangent function in here, you probably immediately think like, oh, this is going to be a periodic function. However, because it is restricted in its domain, that's not something we have to worry about at all. We do need to think about whether it could be even or odd. So to do that, we take f of negative x. Just plugging that in. So tangent of negative x, tangent isn't an odd or even function, but if we restrict it from negative pi over 2 to pi over 2, we actually find that tangent of negative x is equal to negative tangent of x, right? It's going to be an odd function, just in that restriction. So we have negative x times negative tangent of x. Those negatives cancel out. We have x tangent of x, and that's our original function. So this function is even, which means it's symmetric about the y-axis. So this is sort of just the symmetry you think of typically, where if you were to fold the graph across the y-axis, it would be the same on both sides. Now we need to think about asymptotes. So, in terms of finding asymptotes, it's similar to finding the domain, right? We would set the denominator equal to 0, that's cosine. Cosine of x equals 0, and if you remember from that part, that would mean x equals plus or minus pi over 2, plus or minus 3 pi over 2, and so on. That none of those are in our domain, right? So we don't have any vertical asymptotes in the domain. However, plus or minus pi over 2, those are the endpoints of the domain, right? So we are still going to have to respect those asymptotes. They're just not in the domain. So no vertical asymptotes in the domain, but vertical asymptotes at x equals plus or minus pi over 2. So now we need to think about horizontal asymptotes. So normally we would take the limit as x approaches infinity and as x approaches negative infinity of the function. But here, infinity and negative infinity aren't the endpoints of our domain. The endpoints of our domain are negative pi over 2 and pi over 2. So instead, we're going to take first the limit as x approaches pi over 2 from the left of x times tangent of x. So that's going to be pi over 2 tangent pi over 2 from the left. And tangent of pi over 2 from the left, if you think about the tangent function, and this is negative pi over 2, and this is pi over 2, it looks something like that, right? As we approach pi over 2 from the left, the function is approaching infinity. So this is pi over 2 times infinity, which is just infinity. Next, we want to take the limit as x approaches negative pi over 2 from the right. So that's going to be negative pi over 2, tangent of negative pi over 2 from the right. And as you can see from this graph as well, as we approach negative pi over 2 from the right, we're approaching negative infinity. So this is negative pi over 2 times negative infinity. The negatives cancel out and we get positive infinity. So there are no horizontal asymptotes, but this also, what we just did, proves that we do have vertical asymptotes at these points. So no horizontal asymptotes. The next thing we need to talk about is where the function is increasing and decreasing. So again, to do this, we first need to find our first derivative in order to find the critical points, and then to find where the first derivative is negative and positive. So here, f prime of x, we have to do the product rule. So first we do the derivative of x times tangent of x. Derivative of x is 1, so this is just tangent of x, plus x times the derivative of tangent of x. Derivative of tangent of x is secant squared x. So this is our derivative. We want to set that equal to 0. And we want to try to solve for x. So what I'm going to do is try to get a common denominator here. So we know that tangent is sine over cosine. And we know that secant is 1 over cosine, so secant squared is 1 over cosine squared. So what we can do is multiply sine x over cosine of x by cosine of x over cosine of x, and then combine based off of having a common denominator. So this is going to become sine of x cosine of x plus x over cosine squared x equals 0. And from there, we can get rid of the denominator, right? Just multiply both sides by it, and we just have sine of x cosine of x plus x equals 0. Now, we can use one of our trig identities here. Sine of 2x is going to be 2 sine of x cosine of x. So dividing that by 2, we can replace this with 1/2 sine of 2x. So 1/2 sine of 2x plus x equals 0. Multiply by 2, we have 2, or just sine of 2x plus 2x equals 0. So then sine of 2x equals negative 2x. The only place where that happens, in this domain at least, I haven't checked other places, but the only place where that happens is going to be at x equals 0. So that's going to be our critical point. Now, we want to do a number line again. We want to figure out the sign of the derivative on either side of 0. So first of all, we don't care about anything that's less than negative pi over 2 or greater than pi over 2. So I need to pick a number between negative pi over 2 and 0, and then between 0 and pi over 2. I'm going to pick negative pi over 4 and pi over 4 to plug in. So f prime of negative pi over 4 is going to be tangent of negative pi over 4 minus pi over 4 secant squared negative pi over 4. Now, negative pi over 4 is in the 4th quadrant. All students take calculus, only cosine is positive there. And so what we're going to get here is negative 1 minus pi over 4 times 2 over root 2 squared. Now, regardless of working all this out, what we're clearly going to get, everything, both the terms in here are negative, and so this is going to be negative. And then, so we can put the negative sign there. We want to find f prime of pi over 4. That is going to be tangent of pi over 4 plus pi over 4 secant squared pi over 4. This is in the 1st quadrant, so everything, sine, cosine, tangent, secant, whatever, it's all going to be positive. So we have positive 1 plus pi over 4, 2 over root 2 squared. Here all our terms are positive, so clearly the sum of them is positive. So what this tells us is that f is going to be decreasing whenever f prime is negative. So that's on negative pi over 2, right, the endpoint of our domain, to 0, and then increasing when f prime is positive. So that's from 0 to pi over 2. Normally we'd have negative infinity and infinity, but instead we're using negative pi over 2 and pi over 2 because those are the endpoints of our interval. The next thing we need to think about is local maximums and minima, I don't know. And here, just to try out something new, I'm going to use the second derivative test. So y'all can see how to do it both ways. So we found in the last problem that f prime of x equals tangent of x plus x secant squared of x. So then f double prime of x, we just take the derivative of that. Okay, tangent of x, that's just secant squared of x. And then x secant squared of x, we use the product rule. So derivative of x is 1 times secant squared of x. And then we also have x times the derivative of secant squared of x. I'm going to do a little side work to figure out the derivative of secant squared of x so that we can plug that in. So here, both the arguments we're using in this product are secant, right? So first we have secant times the derivative of secant. So secant times derivative of secant is secant tangent. And then we're just going to have the same thing when we do it the other way around, right? Because we have two of the same terms that we're multiplying. So we combine these and also turn the secant secants into secant squareds. We get 2 secant squared x tangent x. So plugging that into f prime of x, I'm going to combine these secant squareds into 2 secant squared of x, and then we have this times x. So 2x secant squared tangent. Now, for the second derivative test, all we have to do is plug in any critical points. Now, we found up here that our only critical point is at x equals 0. So I'm going to plug in 0. F double prime of 0 is going to be 2 secant squared of 0 plus 2 times 0. Okay, so the rest doesn't matter, right? That just goes away. Secant squared of 0, well, cosine of 0 is 1. So 1 over 1 squared is 1. So this just becomes 2 times 1, which is 2. And that's positive. So if it's positive, that means we're concave up here, right? If we're concave up, we have a local minimum at x equals 0. All right, now the last thing we need to worry about is concavity and inflection points. So basically, there's some overlap here where if you use the first derivative test for this step, you're basically just repeating work from the increasing decreasing part. If you do the second derivative test, you're finding your second derivative, which is then going to make it easier when you do the concavity and inflection points part. So it just depends what you're more comfortable doing more of, or just what's easier for that specific problem. So to find the inflection points, we want to set our second derivative equal to 0. So here's our second derivative. We say, oh, what's the eraser? 2 secant squared x plus 2x secant squared x tangent x equals 0. So first, let's just divide by 2. And now we're going to factor out a secant squared. So we have either secant squared of x equals 0 or 1 plus x times tangent of x equals 0. Now, secant squared of x equals 0 means 1 over cosine squared of x equals 0. So we can flip that around to get cosine squared of x equals 1 over 0. Cosine's defined everywhere, right? 1 over 0 would mean like infinity or negative infinity or just generally undefined. And cosine is defined everywhere. So this is not possible. That branch of this doesn't give us any inflection points. Now, we could possibly get inflection points from this. We just need to work it out. So x tangent x equals -1. Let's turn tangent into sine over cosine. I just think things tend to make more sense that way. And then multiply both sides by cosine. So this actually is possible, just not in our domain. If you graphed this, you'd see that it doesn't happen between -pi/2 and pi/2. So we can strike this as well. And what that shows us is that we don't have any inflection points. So if we find f double prime of any number in our domain, then the sign of the result is going to tell us the concavity of the whole function on the whole domain. So we already found f double prime of 0 equals 2 in the last step. F double prime of 0 equals 2, that's positive. So we're going to be positive everywhere on the domain, which means our function is concave up on the whole domain from -pi/2 to pi/2. All right, so next we want to move on to our graphing step. We're there. So first of all, I'm going to draw in, so our x and y intercept are the same, it's just 0, 0. And then we don't have any horizontal asymptotes here. We do have the vertical asymptotes that aren't in our domain but are the endpoints, and so we still have to respect them. And so I'm just drawing those in. All right, we're concave up the whole time. And we know that from -pi/2 to 0, we are decreasing. So I want to start at the asymptote because I know I have to approach it, and I want to decrease concave up. And then we're symmetric over the y-axis, so I just have to reflect that over, which makes sense because we're also concave up over here and increasing. So that fits. And that is going to be our function. So yeah, it's a lot of steps, but this is definitely a useful skill to have and something that's tested often in calculus courses. If you enjoyed this video, please like and subscribe. Thanks for watching, and I'll see y'all next time.